All right, good morning, everyone. Thank you all for being here. My name is Ubieda. I'm the lead firmware engineer at Croxel, and I'm here to talk about application development with TDD, getting started. So test-driven development, it's a discipline that has been growing more popular over the years. But still, we believe at Croxel that there is not enough adoption, or there is not enough awareness of the people wanting to make use of it, understand their benefits, or they just think of it as like a concept that works in theory, but they're not sure if it works in practice. So here I am to talk about a little bit more how to get started, kind of like prove that it somewhat works, and how to apply it in Zephyr. Because on top of this, you have the Zephyr RTOS, which is very powerful, but some people might find it a little bit intimidating. So if you add TDD on top of that, they may not be able to figure out on their own what it's all about with all this complexity. So hopefully we'll break all of those down. I'll give you a good head start on applying TDD for firmware applications using Zephyr. So the agenda today will be pretty short. Hopefully we'll have time to do a live demo. First an intro, then we go over, skimming over the basics of test-driven development. We kind of break it down what TDD in Zephyr looks like. We give a specific detail of just a couple tips of how to fake dependencies in Zephyr, specifically using when you deal with device tree nodes and complex subsystems. Finally, we do a live demo. Hopefully, we'll get something useful out of it, and we will have time for questions. So intro. I studied electrical engineering, but ever since I got in the field, I gravitated towards software. So that is what I found to be my passion, firmware development, very close to the hardware, essentially making software for things that are in computers, electronics, right? So I've been doing that ever since I got out of college. I am the lead firmware engineer right now, as I mentioned many times right now. I only have 7 years of experience. I found a lot of learning and catching up with the new technologies are always coming up. So I'm based in Melbourne, Florida. A lot of people ask, is this in Australia? It is not. It's in Florida. It's the Space Coast. That super nice image that you see on the right is one of the perks in living in the Space Coast, because every other week you have a rocket launch. So you could be getting groceries and you happen to see a Falcon 9 just flying, deploying satellites or something. It's really nice. And the scenery there, it has a lot of engineering vibes, so it's a really nice place to be. You should visit it sometime, not related to this presentation. As I mentioned, I have passion for technology, electronics, and IoT. My first Zephyr contribution, so I'm a Zephyr contributor. Oh, I don't have my tag here that says that I'm a contributor, but I am. My first contribution was in 2021. When I'm not doing engineering, coding, or anything else, I am into fitness and sports. I recently started a blog called embeddedtales.blog, and I have one series that I'm currently working on that's called Zephyr, the Linux for MCUs. Make sure to check it out if you're interested. And nevertheless, I'm a first-time speaker at Embedded Open Source Summit, so please bear with me. Let's talk a little bit about Croxel. What's Croxel? So we are a team of engineers, passionate engineers that do firmware, hardware, and product level design. We provide services. We do consulting. Specifically speaking, one of our strengths is Zephyr RTOS. So we do firmware development. We're big into Zephyr. Most of our applications that we develop for customers are based on Zephyr. We offer different services from product development, end-to-end. People come up with an idea and they say, I want to go to production. We pull together, we allocate a team of engineers, and we develop the solution in terms of hardware and firmware as well. We also are up for rapid prototyping. So you want to show up something to leverage business interest or value. We also are able to do that. Or we can also team up with your team of engineers. You have a team of engineers that you don't feel comfortable with the tools that they're using, or you think you need more. We are able to integrate with your team, do agile, and couple into what your dynamics of their company do. And obviously, we are active contributors in the Zephyr project, and we hope to only keep increasing that contributions over time. All right. I'm sorry. Basics of test-driven development. So it's hard to define what TDD is, and a lot of people have done amazing work to already do that. So I'm just going to mention a few things just to, for somebody who's not really in context of what it is, you can get a glance of what this is, and then just hopefully research yourself. There are books already there that you can check up. Fundamentals for this essentially is like TDD comes from extreme programming. It's totally the opposite of typical waterfall development, where you develop the code base first, and then you attempt to test it to get the bugs out of it. It focuses on incremental development, so small portions of increment, one at a time, and that's the way you build up all the whole progress. And finally, one thing that I believe is really important is that test-driven development embraces the fact that bugs are inevitable. Let's face it, it's not a bad thing. You shouldn't be ashamed of your bugs. You should embrace them, and as such, you need to do something about it. So TDD actually faces that by developing a methodology to systematically catch those bugs, most of the bugs that you usually come up with, because we're humans, we make mistakes. And finally, an interesting aspect is that TDD relies on capturing and passing unit tests as means to develop the application. So you write a test, you describe what the expectation is, you make the test pass, and you come up with the set of tests and expectations. Then you lock in the behavior of your module or your software application so that it passes all the tests. This is an image I borrowed from James Scramning. I personally consider that he is one of the guys who actually brought this TDD into embedded. Essentially, kind of like the life cycle of a bug. When do we usually inject a bug, and when do we know that we have a problem, and when do we fix it? So in a regular development cycle, meaning you develop everything first and you start testing things, the time at which you inject a bug is obviously during development. You have like this set of requirements that you're putting all together this code that seems to be working, right? You run it until you believe, hey, everything seems to be all right, right? Then there's like, we have their TD is the time for you to discover the bug. The time that you know you have a problem. Hey, something's not right here, and everything was working, but now it appears we missed something. And then we have the T-find, which is the time to find what the root cause of the bug is, and obviously the time for fixing it. The time usually between the injection and the discovery of the bug could be days, good if you're lucky, weeks, or even months. Or I would even put it in perspective. You could release these bugs. You wouldn't be able to react on it because it's already deployed. You have customers that are suffering from it. The time to find it, it's always like I guess exponentially, the more time you take to find the bug, the more you're probably going to take to actually find what the root cause is, because you have so many things pulled together. Your mind might not be fresh on what the code that you touched on was doing, and so forth. And the time to fix it, I guess, depends on the root cause. But I guess the hardest part of the bugs, typically, in my limited experience, is that once you find what the root cause is, it's easy to fix it. But it's really hard to really find what it is. Usually, maybe represent or exhibited in different manners that you may suspect other things might be going on. OK, so we are familiar with that one. Let's see this one. Bugs in a TDD development cycle. Usually, and obviously there are exceptions, but in general, what TDD focuses on is, as we're developing the code, we're testing it. We develop a small portion of the code, and we right now make sure that our expectations are met. So generally speaking, when you inject a bug because you didn't do something that you didn't do what you thought you wanted to do, the test will tell you. It will fail, and it will tell you a description of, hey, this expectation wasn't met. So as such, the time between injecting a bug and discovery could be minutes, seconds, minutes. I don't know how long, depending on how long you take to write the test and to exercise that cycle. And the time to find it, it's the root cause. It's also very short because Everything before the last change you made was passing. So you made this last change, this new change, things are broken. What could have caused it? The last thing you put in. It's much easier to find things. And obviously to fix it, because you really know, oh, this is not what I thought, and you just immediately correct it. So I was talking about a cycle, what this cycle is about. So essentially with TDD, you need to get comfortable with tests failing. It's just the first thing. People don't like when their code doesn't compile or something goes wrong. You need to be comfortable with that as long as it is what you are expecting, right? So with the TDD cycle, essentially it's about writing a test, writing a failing test, making it pass, and then refactoring. And then essentially kind of like you start with a list of requirements. And I'm here not talking about like all the application. You should obviously decompose your application in individual modules that have like a single responsibility and a purpose. And those modules that you have broken down your application into have some sort of requirements, right? Then you kind of like transfer what those high-level requirements of your module do. You transfer those to a list of tests. OK, so this kind of like this requirement should mean this and that. And you then put in your tests one at a time, and you apply the cycle of fail, pass, refactor. Red, green, refactor. So essentially, you first might make the test. Obviously, you haven't written any code. You run it. It fails, obviously. You make the minimal change that you can so you can make the test pass, and then you refactor the code. And then you put more tests, and so on. And essentially, kind of like each of those tests contribute to locking in this behavior that we want on the module. And obviously, it's possible because this is agile. So as you're writing the tests, don't try to spend too much time to get all the tests at once before starting to iterate. It's fine if you don't have everything figured out. Some of those things might come along the way. You may realize as you're running the test, oh, I realized that I need this additional test, and so forth. So keep that in mind. I'll give you an example here, just in pragmatic terms. What if we're talking about a software module that goes embedded in a wearable that should detect motion? So I'm here putting a name, motion detection engine. So the ability and the purpose for this module would be to detect what is the device or is the wearable moving? Is it idle, or do we not know? So as a requirement, that's the first thing. The second one would be upon initialization, the motion state is unknown. We don't know what's going on, so we're detecting it. Idle means that no motion has occurred in the last 5 seconds. So if you have your device idle for 5 seconds, after those 5 seconds, it'll tell you it's idle. Movement means, and this is really arbitrary, please don't criticize with this module. Let's just assume that those are the requirements. Movement means that detecting at least 2 meters per square second of acceleration on any axis for at least 1 second. Let's assume that that's the case. And every time we change the state of the motion state, we get a callback, or we get a trigger, an event, so that users know that that's the case. This is an attempt to transfer those requirements in tests. Just pretty similar, but just in a way that now you're thinking about code. So number one, I put that initializing the module starts the motion detection engine. So you just like initialize it and you start detecting it. The initial state is unknown. It's just pretty much a transfer from the requirement. You have a callback, as I mentioned, that you trigger on a state change. How do you bridge that callback to notify the users? OK, that's up to your application design, whatever it's trying to do. For instance, if it's BLE or something else. The transition to idle state if no motion in 5 seconds. So essentially, kind of like the system transfers to goes to into idle state, no motion. You go into movement state if motion is sustained for 1 second. And once entered in motion state, you stay in that state for 5 seconds. So that's kind of like the premise. So you have like a cooldown period in which you think you're in movement state. You probably are not experiencing movement, but you'll stay there as long as you have there. Sustained motion while in movement state extends the motion state. So if you experience motion, 3 seconds later you just move it again, you should like delay the transition to idle state. This is all arbitrary, but just trying to depict an example of what this should look like. We'll come back to this later on the presentation. just like after, okay, so we understand what the cycle is. We just saw an example. Let's talk about dependencies. Here embedded dependencies are really important. Sometimes those dependencies are hardware, pieces of hardware, or so like software stacks and whatnot. So to fake dependencies, generally speaking, you have like a unit under test that you rely on some dependencies to do the functionality you want. And essentially, you fake those dependencies by putting a test double. And essentially what a test double does is mocking or faking the behavior of what your dependencies should be doing so that you can test it without those dependencies. And there are many types of test doubles. In the picture, let me just say, like, the test double actually sets and manages the expectation and returns the parameters. If we think of an API, essentially, you just validate what the arguments you're receiving are those expected, and you just return a response. And those could be of any type. So you could have like a dummy test double, a stub, or a mock. The difference between these three is how fancy or how specific you want to make the test double. The dummy just like, it's there to fake, it's like, it's there, but don't expect too much emulation of the behavior. It doesn't do much. Stub, you start to like putting some logic on this test double, but it doesn't do all of the things. It doesn't validate, for instance, the order at which you call that API compared to other ones. And essentially kind of like it's a halfway. You have some meat on this test double that you want some logic to be emulated on. And finally, the mock is the most refined one, in which you not only validate what the parameters are, the return values, but you also make sure that the number of times you've called this API, the order compared to the other APIs in this module, are the way that they should be. So you can set all these expectations. So dummy, stub, mock, depending on what your needs are, you could use any of these, or just solely one of them, depending. And you may implement these test doubles manually, or you could use a framework to do that. So there are frameworks right now that you can leverage to, hey, I want to mock all of these API, or I want to fake this dependency, and there are frameworks that do that, especially for instance like CMOC, CPPU test, and FFF, which I think it's a function framework, fake function framework, I'm sorry, yeah. So what are we doing this for? What are the benefits? So in a high-level perspective, if somebody just comes in without any context, why would I want TDD? Well, this is why you care. Software development, you can do software development without doing hardware. So like business logic, things that don't really rely on the hardware, you don't need to wait for that to be available for starting that development. You can start that without it. You can catch bugs easier and faster, as I kind of like described before. The definition of done is clear. This is an important point because a lot of times developers, and I'm included myself in that, I've been there before, you're trying to implement a module or an application that does something, and you have the sensation that, okay, once it starts working, if you're doing like develop first, test later, you have the sensation this is working, but I'm not confident that I'm done. So you start to come up with like things that you think should be there, so you add a thing here and there and there and there, so that the things that you're coming up with in the moment are kind of like addressed. But no one's keeping track of that, and sometimes those changes are not exhibited to the surface. So who makes sure that those things don't have bugs, right? The definition of done here is clear, because if all the tests pass and you don't have any more tests to write, well, it seems like your application is done. The definition is done. It's clear. So as such, you improve the predictability of the development cycle. The code base feels less fragile. I'm sure you guys have run into this scenario of, hey, this production code is there, but don't change it too much. And people are afraid to refactor things because, you know, this is working. Let's not question this. Otherwise, it's your fault because you changed it and you broke it. If you have the test suite or the test harness installed and you're running the test all the time, it's easy to know during a refactoring, hey, something broke, and you catch it right away. So the feeling of the code being fragile is not there. You have this safety net to verify that the code does what you think it does. And as such, it improves the overall code quality. Sometimes I run into this scenario where I find a modular functionality that I think it's hard to test. Hey, I don't think this is testable. That is an easy symptom. That is a first symptom that maybe you're not structuring your application well enough. You should rethink the way you're putting the things together so that you can make your code testable. TDD in Zephyr. So apply to Zephyr. What frameworks do we have available? So this is not an exhaustive list, and I see some people in the crowd that are dedicated to testing. Please bear with me, something is not there. C-test is generally used for the Zephyr test framework. FFF is used for mocking. You can use that for mocking. Twister as the test runner, among other things. You also have a radio simulator, for instance, for Bluetooth, which is BabelSim. And now you have PyTest, which is, among other things, you can use for integration tests on top of Twister. This is very subjective, but what I think are the pros and not the cons, but the complexities adjacent to Zephyr. The pros is that Zephyr has a lot of extensive board support. So you can simulate, you can run the tests, not only on a host environment, but also you can running on different architectures and see how the test responds, right? Zephyr inherently comes with abstractions and generalized APIs that do promote a good structuring for you to test your application. So that is a nice thing to build upon. And that we have testing frameworks available and supported by Zephyr. It's not something that you're trying to port and try to make it work with Zephyr. Zephyr offers for those. Not cons, but complexities. People might find intimidating dealing with device tree. It's like, hey, if they're struggling to set a node in the device tree and make things work, how are you going to fake it? It's like it's another step a little bit beyond. And sometimes the subsystems in Zephyr, it's like they're trying to accomplish a lot of things, or like they're a very complex problem. So you might find issues trying to mock all those things. Specifically, additional on top of that, just like the Kconfig dependencies, some people may struggle with, hey, how do you enable or disable, how do I control this behavior? You need to have this control to control what's in, what's out, what's fake, what's not. OK, so when you try to fake dependencies in Zephyr, oh, hold on, just real quick. OK, yeah. I just want to make sure that was there. When you're trying to make your fake dependencies in Zephyr, for instance, subsystems, you may have alternatives. So the first one is that you use an existing Zephyr emulator. Zephyr provides some emulators for you to test with and you to fake the behavior of those modules or those subsystems. So if you think that you can leverage that, don't reinvent the wheel. If it works for you, don't just because you want to have control. It's like, hey, if it's there, make sure you understand it and use it if possible. The alternative is to implement your own test double. And just like here are a few bullet points of how to do that in general terms. So if you're familiar with the build concept, essentially you build individual modules into object files, and then you have this link time step in which all the object files are correlated. So if you have like include directives in the modules, that's where those things are resolved. So the approach that I recommend when implementing a test double is to go for link time substitution, essentially. And how do you do that? Essentially, you make the object file or the module that you're trying to fake, you don't include it in the build. And that means disabling using Kconfigs. For instance, if you're trying to implement like a module that you don't want, you just don't, and implement it yourself. Just implement a test double, link it, and then you can add a minimal test double and implement the used APIs, essentially. Sometimes also like the subsystems may have a ton of APIs. You don't need to fake all of them. You just fake the ones that you expect to use. And that's how you actually fake those dependencies. And one of the approaches for going about it. When you are faking a device tree node, same thing. There are some emulators. I don't have right now the list with me, but if you search through the tree, you will find that there are some. I think you have a SPY emulator, UWord emulator, among other things. So make sure to check those out to see if it works for you. If for any reason you decide that you don't, or that just isn't there or isn't suited for your purpose, you can come up with a test double, for lack of a better name, I called it device tree node test double. And when you are implementing a DT node test double, you just like add a device tree node with the compatible property that matches the faked module driver that you're trying to fake. So essentially, kind of like you implement the property, the fake module as a driver. You make the fake the compatible property. You link it on the device tree node as for instance, as an overlay. And it's important that in your module, you rely on, in the device tree, you rely on, for instance, node labels, that it's easy to fake. So essentially, kind of like if for the motion detection, you say, hey, I want to see just give me the accelerometer, for instance. Give the motion accelerometer. And then that could be linked to an I2C device, a device that's on the I2C bus or in SPI, or it could be a faked accelerometer. Obviously, you check expectations, provide return parameters, whatnot. OK. So at this part of the presentation, what I would like to show you guys is what is that in terms of, so in a pragmatic way, what does that mean? So I'll show you what a test suite is, how to define test cases, and we go one by one just to get the feel for what this iteration cycle looks like. Hopefully you can see my screen. Anybody? OK. Yeah. Yeah. So right now here I put together what module test motion detection. And here we have like the test suite defined for this. The name of the suite. We have a single test case, for instance, just for verification that the hardness is installed. And here we have a few things to consider. Every time you execute a test, you have like a function that executes before you execute the test, and then you execute another function. Sometimes you call that setup, execution, and tear down. But the nomenclature may vary. But in essence, that is what it does. And here I have, like in a comment, just a list of tests that we had written on the slides before. So let's do a couple things just to get the feel for what that looks like. I have here. Let me see if I have it over here. There you go. So I'm going to build this command. You could use Twister for this. I'm just going to use what's built just to get the instant feedback on the screen. But you could use Twister to execute simultaneously many test suites in case that is something that you're looking into. So just build it as an application. So essentially, you have the module, but you're using the module on a separate application, not the one you're trying to develop. And essentially, you just run it, and the result looks like this. Essentially, you have a single test that passed, and obviously this test passed because our expectation was that it was true, and we set it to true. That's just to validate that the hardness is installed. Everything is in place. Now we can work on top of this. So let's find let's say that we do this test. And I'll probably just copy paste this a few times. Let's say test init OK. And let me start simple. Let's say that you have the expectation is to have something like this. OK, so this is very simple. The goal here is that we have an API, an initialization API, and that it succeeds, meaning that it returns 0. We just wrote it. And obviously, it doesn't work because we haven't done anything with it. So the steps here is that first, you detect that you have an implicit declaration. Obviously, we don't have it defined in our header file. And I'm just going to go over here. As you can see, this is an empty file, motion detection. So I'm just going to do then we iterate once again. OK, let's see. Now it fails, but not because we have an implicit declaration, but because we don't have a definition for this. It's what we expect. If it failed for any other reason, stop, figure out what is going on. In this case, it's what we expect. So right now, I'm just going to do the slightest thing to make this thing pass right now. So my subsystem is defined over here. And I'm just going to do this. New line. And it passes. So, okay, but the code is not doing anything, right? But we have verified that we've installed this new API, that it's there and it's doing nothing, but that's the job of what we will do next, right? So, for instance, what if we say, let's do, so just one thing I wanted to mention as I'm going through this. Obviously, as you're developing the test, you should have an idea of what the behavior should be. So this is not a replacement for sound design. So you should have like kind of like the idea of what you wanted to do. And as you're going through the test, you force the test to go in that direction. So it's like, it's not about not thinking what should be doing, but actually kind of like having an idea. I hope that is clear. And so let me just go on with detection, test suite. And let's say that initial state. We can do, so which test are we going to do? We're going to do callback gets triggered on a state change, let's say. So essentially, we initialize once again. We can verify that this is OK. And then let's assume that we have a expectation is that we have, let's say, have an enum with a new state. And this could be so essentially you just keep track of this. Let's say that OK, so every time we get that callback, we'll get that little increment. So after we call this, we should verify that state change it's equal to 1. And that is our expectation. This doesn't fail. And it doesn't fail because we don't have the enum type defined. That is expected. So right now what we do essentially is just define let's just put something here, invalid, and now we just try it again. And this time it did work. It did, I mean, work in meaning as in it built and it ran, but it failed. And the reason why it failed is obviously because the motion state called is not 1, it's 0. It's not doing, it isn't doing anything. So we just do the lightest thing to change this behavior. And for instance, essentially kind of like we're relying on this callback, right? But nobody's calling it. So I guess one way to go about this would be to say motion detection, for instance, and we just pass on this function. Let's say that we have this API that we called before. We run it again. We made a small change. We verify that now this API obviously is not declared. So we declare it. And for what I'm going to do is I'm going to define let's say that this is the handler. Okay. Still, we fail because we don't have this API defined. So, oh, sorry. And then we can simply go in here. So I can just run it again, and now we don't know what this type is, and it's because we haven't included motion detection. Now included. Hold on. Oh, I mistyped it. So this type of errors just happen all the time. And this time, as you can see, as I'm making these mistakes, I'm figuring them out quickly, right alongside, as I'm writing the test. So it now runs again, still fails. And now let's make this slightest change to make it work now that we have all this in place. So let's say that we have this internal that we have in here. And let's say when we initialize, let's say that we just call it. We just receive the parameter. Let's say that it's this, just for sake of this. And it passes. This time passes, and the code doesn't look to be complete, but it's written by the test. As by the number of tests that we have right now, it's passing them all. So the idea is to then add another thing and another thing on top of this. And we can continue going on. I would like to have a few minutes just to have questions. So what I'm going to do, I think which branch and I am. So I prepare this ahead of time. I have like a set of like what does it look like if you just work on it for a while. I'm just going to, hold on. OK. It doesn't matter. I'm going to check out to demo TDD to rebased. Let's check what's going on here with Git. Oh. OK. Let me close this, don't save it. So after a while, if you've been practicing TDD, this is what the test cases should look like. Hopefully you guys can see it. The time I did it was motion aided OK. We initialized it, was OK. And we had another test case for when enabled. So if you enable it while enabled, you essentially kind of like you have a response that, hey, you already enabled it. That's one thing that, as we came across, I put it in place just to make sure. If you initialize it, starts the engine. So now there's an API. I came up with an API to say, hey, is this enabled? If it's disabled before initializing, you should see the state. I'm sorry. If it's not enabled, you should see that the state is disabled, and so forth. So this code is available for you guys to check out on public repo that I'll redirect you to. But essentially, kind of like here is an interesting case where you have make sure that the accelerometer, for instance, pulls once a second. So in this case, I came up with a test double for the accelerometer, implementing what I described. So you have this driver that you initialize as such. It complies with the sensor driver APIs. In this case, I'm relying on sample fetch and channel get. And it's just emulating the behavior of it. So as, sorry, going back to this. OK. Yeah, so as we're going back to this, you can make sure that the accelerometer has been called once with channel sample fetch and channel get, and so forth, twice, 3 times, and so forth. OK, so the good thing about this is that simultaneously, as essentially once you have like the test written and everything seems to be working, everything passes and you think you're done, it's easy for you to test it. For instance, the motion detection, just to validating on hardware. This is what the API looks like if you've finished and you've gone through all the tests. And I put together a sample. So essentially the sample is very simple. You initialize, you add a listener, and you initialize motion detection. And it's just going to print out if the state changed. Let me see if I can quickly just run through that. I think we're running out of time, so let's see how fast can I do this. I'm going to be using a board that has that is battery powered and has an accelerometer on it. I'm going to use Bluetooth to see the console on it, so I can check it out. So we're pulling it. OK, so it's flashed. I'm going to use Bluetooth to see what's going on here. Hopefully. OK, there you go. So the messages that are here are on this battery-powered device with this stuff that the module we developed with test-driven development. As you can see, it's now set to movement. Let me see if it's now idle. Move it, movement. Idle again, I move it, I keep moving it, and it should not transition to idle state, as our expectations are. Seems to be working. So TDD allows you to make sure what you think you're doing, it's happening. Now the question, is that the right thing? That's another question. But at least from what you think you're doing, the code will be doing what you think you're doing. So it allows you to rethink what should the code then be doing, so you focus your attention on that. Yeah, that's all for now. I'll redirect the repo. It's there right there. You can see it. And it's public. You can check out the sample with all the test cases captured in detail, plus the sample. Thanks for your time. I'll have some questions briefly. Any questions? OK, yeah, I was hoping you weren't overwhelmed by my presentation. There was a lot of stuff. Sorry. OK, so I can still hear the.
Also, that your experience to test, to be able to get code coverage, to test code, it has to be driven out of main and into, if you like, libraries.
So I'm sorry, could you repeat the question?
Yeah, you can't actually test code in main.c, if you like.
So, OK, yeah, so unit testing focuses about units, right? Yeah. It's about module and a thing. I think that doesn't exclude other types of testing, like integration testing. Yeah. So essentially, this allows you to build the modules that do like the purpose and like dedicate, for instance, motion detection. You wouldn't be dealing about accelerometer or I2C transfers or anything like that. So that allows you to what are you going to do with that information, and maybe some other types of like testing, testing integration testing will be better for that.
Okay.
Yeah.
Thank you.
It's great for libraries and modules and subsystems, like have a dedicated purpose.
Okay, thanks.
What? Oops, okay.
Thanks. I was wondering with the the test stub for the accelerometer, you had a test that made sure that it worked every second. You run a thread in your test module that does that?
Yes, let me show you that. Yeah, so as a response to that test case that was captured, in this module I define a thread, and essentially this thread, the simplest thing I did was just to insert a 1 second delay, and every time you just sample it, and I just put it in like in a history buffer, just keeps track of what are the latest samples. In this case, ended up being 5 samples, so essentially that's all we care about, right? Is there motion in the last 5 samples or not? And essentially that's how it came up to be. Yeah, it's unfortunate that I didn't have time to go over it. I wanted it, but still the code is there. You can check it out as the link I shared. Any other questions? Yeah.
Thank you very much. Oh, there's one more. Okay, and then I think this is it. Okay.
Last question.
Does this approach work with drivers that interact with memory? For example, if my driver is reading or writing memory, will I be able to write a table for the memory? And
yes, it works. Yes, and I believe later today there will be a presentation about that. I'm not sure. Yes, it does work. There are ways you can fake memory map devices, so it is possible.
Okay. Well, thank you very much.
All right. Thanks, everyone. Appreciate your time. Thank you.